let's just talk about what a conductor is. We'll then come back to it. Conductor. I didn't say ideal conductor. I'll just do medium in which the electrons move. I'll put freely in quotation marks here. Actually, I guess if it's ideal, they will move freely. Reality is that electrons move, unless you're doing superconductivity, the electrons will bump into things. And then the opposite of a conductor is an insulator, an ideal insulator, a medium or material in which the electrons don't move. Now, in reality, nothing is pure conductor or pure insulator. You can conduct electricity through a lot of things that are generally considered insulators. It's just hard.
So, is an insulator, they don't move or they can't move through that thing?
If for the atoms in an insulator, atoms in an ideal insulator, the electrons won't. They'll stay with their atom. Okay, so since no one was willing to take a chance there, except for Jack.
Or it blows up.
At least we're getting video of it. Jack was right the first time, then he started hedging his bets. Come on. As I pull this away, what's going to happen?
Go back to normal.
Anyone else?
Oh, well, depending on how far you move the stick. Good. Yeah.
Is that normal?
It looks like it was before. From what I can tell.
Well, one way that we can tell is if I just touch it. They move slightly. It didn't go completely back. So why did they not stay far apart?
They got more electrons from set back because they transferred.
Yeah, but why did... All right, let's do another scenario where they're going to stay farther apart, because this is January and not May when we're doing this. What was the difference between what I did the time before and this?
They can rub their cost.
Why would that make a difference?
There's more being transferred.
Why were they not transferred before?
Because it was only the one impact that gave it the transfer.
Why did the others not transfer? You're right. Why did the others not transfer? What does the rubbing do?
It gives it more points of entry.
Okay, so why did, I mean, it's still, they're all still going through the same spot right there.
Right.
Why does just touching it only transfer locally and not from the entire piece of PVC?
Because it's kind of like a crammed subway station.
Wow.
Like everybody's trying to get on the subway car, but when all the doors open, and that being there, more people are. See where I'm going with that?
Yeah. I don't think that's the best analogy on that one, but I'd have to think about that a little bit longer. What was that?
You said oxygen triangle. Insulators.
This is an insulator. What does that mean?
Oh, so they don't move freely until you move it across to that specific point.
Yeah, so we have only one point of contact the first time, but because it's an insulator, these electrons are going to basically try to stay where they are. Now, this is sort of extreme language. Again, no such thing as an ideal insulator. It will draw from more than just that one point of contact, but not very far. All right, so now we have excess electrons on here. That's why the leaves are staying apart. Now, if this were, I've done this in May and June, and the leaves would already be back together by now. Why is May and June a horrible time to be doing this demonstration?
Humidity.
Exactly. No, that is it. What can you tell me about what is humidity?
Water in the air.
More specifically, not just water.
Vapor.
Yes, thank you. And what can you tell me about a water molecule?
There's hydrogen
Yes.
and oxygen.
Okay, how many of each?
There's H2O.
Okay, which tells you what?
One hydrogen, two oxygen.
Two hydrogen, one oxygen.
Yeah, I assume that's what you meant. How is the water molecule oriented?
It's like a triangle.
All right, so I got my oxygen right here, and I got a hydrogen here, and a hydrogen here. Hydrogen's just a proton and an electron. The electron is hovering over here, which means that this side of the water molecule is positively charged. Over here, I've drawn 2 electrons over to, well, I have 2 electrons there, but I still have 6 electrons, so that side is mostly negatively charged. It's not as extreme as I'm presenting it, but it's something like that. This is a dipole molecule, or polarized molecule. So there's a positive and negative sides, which means that, oh, I got a positive side here, the electrons get attracted to that side. So in humid weather, they will collapse. And in the first lab that you're going to do, one of the checks you're going to have is you're going to charge this up and see how fast those leaves move together, because that will determine how much you can do later on. There's some shortcuts you can take if it's dry, and some shortcuts that you definitely cannot take if it's humid.
Tomorrow it's gonna rain.
Was that?
Tomorrow it's gonna rain.
Well, fortunately, I'm hoping not inside.
Oh, okay.
That's the dream. But yeah, if it's raining outside, that could affect it. It's just a question of how much water vapor, not necessarily how much water. So that's one of the reasons why I commented on that. Raining is not necessarily 100% humidity down here. So how do I get the leaves to go back together? What does that do? It disperses?
Yeah.
What disperses?
The electrons
Where do they go?
to you.
Yes. I'm known, basically, in this particular small example, I would be the ground. If you have a huge object, relatively huge object, then I'm a source of electrons or I'm a sink of electrons. Because that has excess electrons, I can take a whole bunch from that. There are other situations in which it is, I would be a horrible ground, such as a power line fell. It would probably, I would be a conductor in that particular case as the electricity tries to go to the actual ground.
And that hurts.
What's that?
I said, and that hurts.
If it's a power line, I'm not quite sure it hurt for long. So, I'm going to say Milagros?
Yes.
Did I pronounce it even closely?
I go by Millie.
Millie? Okay. And there's no one else I recognize. So we were missing 4. I wonder if they're across the way.
Is
Wait a
lab
second, this is
same
one of the
place?
Pardon?
Is lab in the same place as last semester?
Yes, I think it actually is officially in our room, as opposed to before we just moved down there.
So we saw the hydrogen, or we looked at the water molecule, and we said that because the hydrogen side is positive, because it has one.
All right, so the hydrogen atom has a proton and an electron, and at its base level, the electron is indeed zipping around and
Okay.
so fast that we really can't tell where it is unless we try to look at it. Because the electron gets shared with the oxygen molecule, oxygen atom, we're left with basically a a positive charge there.
Okay.
So basically, it's hovering around, so it's neutral from all sides. The electrons just likely be here as here, but when we throw the oxygen into it, that electron now is hovering mainly over here,
Okay.
basically stripping away the protection from down this way.
And making it positive.
Yeah.
And then the oxygen is negative because it has more electrons.
Yeah, it has 8 electrons, and so 2 of them are being shared down here, but we've got the other 6 that are hovering around primarily out over here.
So is that something we're gonna have to like almost memorize, like the amount of electrons each?
No.
No.
You just recognize that it's a dipole molecule, the fact that it's polarized, so I got a positive and negative side. And that's sufficient.
Awesome.
Yeah.
High school chemistry.
All right. However, let's separate this from high school chemistry. Because I know what you're all thinking. It's a thing that you'll always think, where's the math? Yes. Let's do the math. Yes, that's right. Since there is attraction and repulsion, there's a force involved. That is a sad one. Is there a trash can? Oh, can I do this without hitting a leaf?
We're not leaving it to the floor this time.
That was so bad. So whatever formula I come up with here, I know that if they are
You might end up throwing it on the floor now.
the green one, there it is. So whatever formula I come up with, it has to take into account that if they are negative charge, if they are opposite charges, it needs to attract, and if they're same charge, they need to repel. I know that if I have a positive and negative charge, that force between them, if I flip the direction around, it's still the same magnitude of force. So commutative property needs to hold. And again, there are 2 math functions we have, 2 basic math functions we have, where commutative property holds.
Multiplication.
And
Addition.
but we want the multiplication one. So we have a force, an electric force, so now I'm going to use the subscript E for those who have had me before. I did not use E for elastic for this reason. So this is the electric force on charge 1 from charge 2. U1, U2. All right, so we got the product there, and if I flip 1 and 2, the magnitude doesn't change. It also depends on how close it is. When I had this thing negatively charged, how many of you felt that negative charge? Besides Jack. And Ellie. Ethan, how'd you feel it? Do you think if I brought this thing close to you, you would feel it?
Probably not, no.
You still? Because I'm dead all over. That is incredibly unimpressive. I feel it, but the hairs aren't moving a whole lot. There's a little bit of a rustle in there. Well, actually, we can demonstrate it from here. This thing is negatively charged. The leaves are not reacting to it yet. At some point, they do start to move. So there is something about distance that has to be involved here. The closer I am, the greater the influence. So as R gets smaller, the force gets bigger. That goes on the bottom. And part of the lab that you're going to do is you're going to actually test to see if that really is squared. And then we have a unit issue, so we stick this number up front. This looks a whole lot like the gravitational formula. Anyone remember the generalized gravitational formula?
There's a big G in there.
Yes, there is. Let's ignore the signs at this point. Big G.
M.
G. You want to bring in the little g?
Yes.
Yeah, let's hold off on the little g.
Big G again.
Or not.
Or not.
What's there required in order for there to be a gravitational force?
Oh, a big object and a small object.
Well, in that case, two masses.
Two masses.
M1, M2.
Oh, yeah.
There's divided by.
Yeah, divided by something.
M. 2.
Distance.
Squared. R squared. I'm glad it had that much of an impact in your lives when I talked about this last time. Or longer ago. Notice the similarity between those two formulas. And that's about as far as the connection goes, as best we know. It's in the theorist's hands at this point. And they're just throwing stuff up against the wall and see if it sticks. However, when I was in grad school, I had access to the proposed South Carolina high school graduation standards. So I flipped over to the physics section. And in the physics section, for the proposed standard, they said, express the electric force in terms of the gravitational force. Now, I think the intent was that they wanted us to notice that it's an R squared, inverse R squared relationship. I got, and you're multiplying 2 of whatever the quantity is, masses or charges. And it made me laugh, and I mentioned it to my advisor, and he said, yeah, you got to graduate from a South Carolina high school and win a Nobel Prize at the same time. It did not make the final draft, but I thought it would have been funny had it done that. So South Carolina could claim it had the toughest standards in the world for high school graduation. So anyway, Q represents charge. Big Q represents charge. The difference is you tend to do little q when you're talking about a single charge, and you talk big Q when it's a collection of charges. This is a common standard. However, I will use big Q, little q interchangeably, just because. Childhood scars as always. So this is a collection, and this is single. That's the general standard, but there's some gray areas that get messed up in that, so it's not 100%. All right, what's missing from my formula here?
You said what's missing?
Yes.
There's something missing.
Yes, there is.
Is it outside of the division symbol? Is it like
Yeah,
plus
it is
minus
outside this.
something? Like
No, not plus or minus anything.
Take all of it and square root it.
And then whatever you get, square it.
Yep.
Think back to the beginning of 151. I think it was probably the first topic, if not the first, the second topic.
Is it those cake equations?
No, before cake.
Before cake. Oh, my brain's not too good. Okay.
Cake refers to constant acceleration kinematic equations, like Vf equals Vi plus At, Vf squared equals Vi squared plus 2As, or delta S. And person who just came in, what is your name?
Jordan. I'm sorry I was late, but there was a car accident on the highway and there was traffic and I could not get out of it.
So he caused a car accident, using that as an excuse.
No. I emailed you that.
I'm glad you could make it.
Yeah.
All right, what's missing?
Equation for force.
Vector.
Say it again?
Vector sign? Vector sign?
Ah, it's a vector. I got the vector sign on the left-hand side. What's missing in general?
The vector sign.
What is a vector?
A direction.
Okay, not really the definition, but yes, that's the piece that's missing. We're missing a direction over here. So again, we need to set up somehow so that if they are opposite charges, they are attracted. If they are same charge, they will repel. And so we stick on R to hat at the end, and we are done.
Not the prettiest of equations, but I see there's an appeal.
One of the differences between this, if we threw the vector bit in here, so 1, 2, R to hat, there'd be a negative sign in front there. Because the force on one, if masses are always the same sign, it's not necessarily down.
Oh yeah, that's right.
So
The masses are always the same sign, so this quantity right here is always positive. And they're always going to be attracted, so the negative towards, that negative sign means towards 2. Whereas over here, if they are opposite signs, this whole quantity will be negative, so it will be towards 2. If they're the same sign, this will be positive, which means away from 2. If you recall the radial unit vector, and which is away from center, and you have to define where the center is, and negative r hat would be toward the center.
So
Cetar.
if the division symbol is positive, like within the things inside that division symbol are positive, R is going to be negative, or the other way around?
What, that right there, that r?
No, the R hat.
Although that's always a positive number, it's just a matter of whether this is positive or negative.
And
All right, so let's actually do a plug and chug. Any questions up to here?